We'll get started with the first question, right? Let's go, Eric. Okay, yeah, so here's what you'll get, right? Just to quickly summarize the things you'll get for the from this webinar. So if you don't have enough time to take down all the notes, don't worry. We're going to send you guys a webinar handout with all the solutions written out, okay? And we have a preparation SAC package as well that we do offer at a discount for you guys who are joining the webinar. And yeah, if you guys do want to subscribe to our email list, it's on our website. You can, I think Eric might put in a link as well. It's on the main website of the company. Just scroll all the way down and you can submit your email so that future notification for such webinars or other resources content you'll have access to as well. So, okay, so part one, we've got multiple choice questions. Okay, we'll start with something nice and easy. Question one, a stationary coil consisting of 20 loops, okay, with an area of 10 centimeters squared is placed on a uniform magnetic field. All right, you can see the illustration there. And it's got a B field around it that's got 5 milliteslas, okay, in strength, okay? Uh, and it's placed there for 100 milliseconds, okay? Where the plane of the coil is perpendicular to the field direction. The field's running left to right through the loop. What is the induced current flowing in the coil? We'll start off with this one. I'll start a timer on my screen for 1.5 minutes, and feel free to have a try. So if you've got an answer, you can message us as well privately, uh, the answer and why you think that's the case. A few seconds left. All right, great. Time's up. So we've got some answers. I think we've got a split response here. But if you answered A, that's the correct answer, you're correct. So I'm just going to try to see if I can annotate. Oh, can't annotate. Hmm. Okay, there we go. Let's see. Right. Okay, so A is the correct answer. Okay. So hopefully some of us got that. If you got A as a correct answer, 0 milliamps is the correct answer. Very good job there. Okay. There is no current that's induced in the coil. That's the correct answer. Why is that the case? So it's very easy. You see this question and you're like, okay, there are some numbers for the loops, the area, B field, and immediately we want to jump and use equations. So we look at the Faraday's law, right? EMF equals delta phi or negative N delta phi on delta t. And we might be very fast to go and sub these numbers in, okay? But however, remember guys, if you want to generate an EMF, okay, we need a change in flux over time. So over time, the flux needs to decrease or increase in order for a current to be induced to compensate for that change. In this case, we have a static B field, right? It's a uniform and static B field. Okay. And because it's static, right? Initially, the amount of flux passing through the coil is the same as, a few minutes afterwards. And because of this, we have no change in flux. And so A is the correct answer. Okay. So, yeah, it's the first question. Let me know if you've got any questions. Okay. You can message it in the chat. Otherwise, we'll move on to the answers in the next question. Okay, cool. Let's move on. So question 2, let's take a read. You've got a coil now. Clear the screen here. With an unknown head shape. Okay, so the shape of the coil that enters, so you can see a coil on the left-hand side. Okay, so you see a coil here, and the shape of the coil is unknown. Okay, and it is going to enter into a B field at a constant velocity. So you want to, and the graph of the EMF, right, versus time graph is shown on the right-hand side. The question is to select the correct, shape of the coil that enters and exits the field. Okay, so same thing, guys. I'll give you guys a minute and a half to have a try. And again, shoot us through the answer you choose and explain why. And we'll review in a second.
I just want to point out for those who think it's a very hard question, folks, indeed, it's a very tricky question. That I think you're getting some sort of advantage if you know about something like calculus, that may help. But yeah, in the solutions that we're going to walk through in a short bit, there is no need to utilize those things. We can simply understand the physics. But yeah, it's a very hard question, right? So give it a good thought and feel free to share your answers in the chat room. And not just the answer, I want you to explain, right? Why would you think in such a way, right? So we want to see the explanation part as well. Okay, about 1 minute left. So I'll check the chat. All right, so Ralph, you can keep talking to the students. I'll be monitoring the chat.
Cool. So we got some pretty good answers. I think a lot of us didn't choose C or D because C and D is probably wrong. Okay. I think some of you guys chose the correct answer. So the correct answer is B. Okay, B is correct. Okay. And we'll explain why that's the case. So keep in mind, right, we're dealing with an EMF time graph. Okay, so EMF over time. And to be able to solve this question, you really need to understand what determines the EMF at any given point. And it comes down again to the Faraday's law equation, right? So EMF is equal to negative N delta phi on delta T. Okay, so change in flux over change in time. So what does that mean? That means at any given change in time, so Eric, if you think we disconnected, yeah. So I think I think we zoom out, I think it might go away, but all right. So with any given change in time, so for example, we for any given change in time, so in any given fixed set of time, okay, if you have more change in flux, if you have more change in flux in that same amount of time, right, you have a greater EMF. Okay, so if the delta phi is greater, okay, EMF is greater. If the delta phi is lower, right, if lesser change in flux over time, then the EMF you generate is going to be lower as well. So EMF is tied to the amount of change in flux per given time. And so what happens is if you look at this, diagram on the EMF diagram on the right, the shape of the EMF change goes from very little to very negative and then back to very little, right? And then that's when the coil enters into the magnetic field. And when it exits, the same thing happens, except it's on the other side because the change in flux is in the opposite direction, right? You start off slow and you reach a maximum and you go back down to a minimum as well. So the way you look at it is the magnetic field is cutting your coil, okay, at any given point in time. And in option B, right, imagine you're cutting, this little section of your coil. If you're cutting this little section, the amount of flux that passes through that very little corner of your triangle is very small at the start, right? So because of this, we'll have a small EMF generated at the start. And as the coil is moving through completely into the magnetic field, let's say somewhere in the middle, okay, let's say it's somewhere in the middle. Well, now the amount of flux that you can cut with the now taller shape of the wire is going to be greater. So this slice, you can imagine slicing a cake, okay, horizontally as you're going. Initially, the slice is going to be very small, right? Somewhere in the middle, you're going to get a very long slice, okay, because you're capturing more of the area of the cake. So same thing here. In the middle, you're capturing more of the flux. And so the shape of the EMF time graph should be related to the vertical area or vertical cross section that your coil shape is in, right? So in this case, a triangular shape would give you a triangular change in flux over change in time, and therefore EMF over time. Okay, so something like a semicircle would give you a semicircle shape, so on and so forth. You're looking at the cross-sectional kind of slice area that your coil can cut field lines for. In this case, it goes up and then it comes back down. Okay, so B is the answer here. I've got questions. Okay, let me know. So any questions from anyone here? Okay, I'll take that as a no. So you can always message us. If you've got any questions in the chat or otherwise. Um, if we're happy, we can move on to the next question, Eric. Cool. Okay, so question 3. Okay, got a question. What would the EMF time graph of the circle look like? That's okay. Good question. So the question is, what would the EMF time graph of a circle look like? So circle would look like this. So initially, as you're entering, imagine the circle loop is entering into a magnetic field. The field cuts the circle like this, right? It's going to the left and it's cutting the circle like that. So initially, right, the first slice is going to be very, very small flux slice, and the next one's going to be bigger, and then bigger and bigger, and so forth. So your EMF time graph would look like this, right? It's not exactly the shape of a semicircle, because you're really doubling up, the circle into twice the height, because, the circle has 2 semicircles. But yeah, it'd be a curved kind of parabolic shape, yeah, above the midline. Okay. Cool. So great question then. Let's move on to the next question. It's question 3. All right. A resistor is connected to a sinusoidal wave voltage supply. The RMS power delivered to the resistor increases from 5 watts to 10 watts. Okay. So from 5 to 10. What is the new peak power being delivered to the resistor? So same as before, we'll give you guys a minute and a half to have a try. So the timer starts now. And once you've got it, get your answer, feel free to send it to us as well, message us the answer, and we'll reply to you. Okay, so a few seconds left, guys. I think quite of us gave some answers. We'll chat about that in a second. Okay. Cool, very nice. So the correct answer, guys, if you chose D, that's the correct answer. So congratulations if you chose D. Okay. Um, so there's a formula. Okay. So formula is that PRMS, okay, is equal to half of peak power. Okay. So peak power is twice that of peak RMS. Okay. Why is that the case? Well, we all know the formula for peak voltage or peak current. Hopefully, we know that by now. Okay. So there's a formula for peak current, right? I peak, for example, is equal to RMS current divided by, so no, multiplied by root 2, okay, IRMS multiplied by root 2. All right. So I peak equals IRMS multiplied by root 2 because RMS is kind of, you can kind of think of it as the average. It's not exactly the average, but it's kind of the average. And when you multiply by root 2, you get a higher number, which is your peak amplitude of your current. Okay. So you can think of a diagram, okay? Current time graph looks like this. Your RMS is the average, right? It's roughly 70%. That's your current RMS, okay? Your peak current is going to be, the amplitude of your sine wave, okay? And so that's the equation for I peak. And a similar equation exists for voltage. V peak equals voltage RMS, okay, multiplied by root 2. Same thing here, okay? So the thing is, we look at the formula for power. We know that power is equal to current times voltage. And so it makes sense that peak power, P peak, is equal to I peak times V peak. Okay, if we sub in the two equations we've had at the top into that third line, V peak equals I peak times V peak, which gives us I RMS times root 2 times V RMS times root 2. And so this simplifies down to just 2 times I RMS times V RMS, which gives us just 2 of peak RMS. Okay, so that's why in converting peak RMS to peak power, we don't just follow the traditional multiplier of root 2. We don't multiply divide by root 2. We multiply divide by 2 because of this derivation. The root 2's combined together to give a 2. So from 10 watts, that is the RMS power at the end. The peak power should be 2 times that, okay, or 20 watts. So that should be our final answer. So same as before, if you've got any questions, feel free to shoot us a message and we'll answer it for you. Um, Otherwise, we'll move on. Maybe a few seconds for you guys to copy this down and absorb it. Otherwise, we'll move on to the next question, question 4. Cool. So this is the last multiple choice question. Question 4. A transformer is designed with a soft iron core. Okay, so you can see that here. It's very classically represented in any transformer. We haven't studied as much about what it's for, so I think this question really tests you on that. What is the most likely outcome if the soft iron core is removed? Okay, so option A, the transformer will no longer transfer energy. Right, B, the transformer will still work very efficiently. C, it'll still work, but with reduced efficiency. D, the transformer delivers more voltage, all right? Because the missing core reduces the resistance to your current flow. So same as before, I'll start a timer for a minute and maybe a minute for this one, okay? And if you get the answer, shoot us a message so we can see. Okay, cool. So that's our last multiple choice, for the day. And the correct answer, I think most of you guys got it. The correct answer is, in fact, C. So that's the correct answer, and that's correct. Okay. All right, so the transformer will still work, but with the greatly reduced efficiency. It just wouldn't be as efficient. Why is that the case? So, to answer this one, you have to understand the purpose of the soft iron core, right? What is the soft iron core there for, right? It's there. Its main job, we'll write it down, is to amplify. Okay, to amplify the B field or the magnetic field, right? So imagine if you've got this, primary coil and the current is coming from the bottom, right? Okay, and it loops all the way up like this. Okay, okay, and comes back up. If you use the right hand grip rule, the coil rule, the kind of the extended or the augmented one, then your thumb is pointing upwards, which means that the magnetic field passing through this coil is going upwards. Okay, so you'll have an upward magnetic field, B field, like this. And it comes back in from the bottom like that. Okay, like this. And so what that means is there's a circular shape of magnetic field that goes around like that and passes through the second coil on the right-hand side that goes downwards, right? The soft iron core is made out of iron, okay? And it's made out of a type of iron that's very soft, right? What that means is that the magnetic moments, you can imagine all the individual magnetic elements in the soft iron core can turn, they can rotate, and they can align themselves with whatever external magnetic field they're in, right? So if they're in a magnetic field that is going up, they'll align themselves upwards, okay, to magnify or amplify the magnetic field. If they're in an external magnetic field that's going down, similarly, they're gonna, align themselves to magnify this downward magnetic field. Okay, so the purpose of the soft iron core again is to amplify the B field. Okay, and so it makes the transformer a bit more efficient, and that's why we use it. Okay, so if we lose the soft iron core, no worries, we're still going to produce B field. That's going to pass from the first coil to the second coil. It's still going to happen. It's just less efficient because we're not amplifying it, right? So imagine you're, speaking in front of a podium or a stadium, and you've got a microphone. The soft iron core is the microphone. It amplifies your volume with speakers so that people can hear you clearer, okay? If you don't have the microphone, you don't have a set of speakers, it's still fine. People can still hear you, but just less loudly because you lose the iron core, which amplifies your signal, okay? So C is the correct answer here. And yeah, that's it for question 4. Any questions from you guys? Okay, I'll take that as a no. Yeah, cool. Right, happy to move on to the next part, Eric.
Yeah, and to the next part, it will be the high yield structural questions. So I'm sure all of you have done the warm-ups, right? Thanks so much for the heated discussion we have, in the main chat and also the private conversations I'm having. It's been amazing to see, how we all contributed to the correct answer. Let's do the same thing here. Let's keep the energy high. Let's do the same thing for the high yield structural questions. So we have 3 prepared for you all. Just look at the time where we may try to do the best ones we have. Let's say we're going to do 2 in very, very detail so everyone understands how to do it. In which I'm going to show you guys a scenario first. And here you go. This one is a 9 marker. All right, it's very classic question, but I would say with a twist. Okay, so it's not exactly the same thing you see all the time. Let's do parts A and B all together, right? So, Raf, I think it's good to give the students about like 3 minutes in total, right? Just to give a good thought, all right? And read the question very carefully, right? So, 3 minutes for 2 questions. The goal, guys, the goal is not to get every single mathematics and every bit correct, right? The goal is to train our ability to decipher examination type questions, right? That is to read and comprehend what is written in there. All right, so 3 minutes. Once again, any questions, anything you want us to clarify, I'll be answering the chat. Okay, so shoot the questions, yeah, to us. And so we're about halfway there. I'll drop some hints for those who are still thinking about how to do the question. All right. 270 degrees. It's a bit of an interesting number. Okay, so you're gonna think about, using what you know before, right? Usually questions ask about 90 degrees, right? How to use that piece of information, all right? And then change it into 270. So that's why it's a classic question with a twist. So that's the part 8 hint. We're gonna check our answers in about a minute. So I will mute myself and have you guys give it a good think. Alrighty, let's begin. Okay, so I actually got a message from one of you saying that the 270, it's like a trick question because guys, if you think about it, all right, for 270, right, usually questions ask about a coil, right, that's turning maybe from this state to like a vertical state. So that is like a 90 degrees of turn, right, along the axis, so that's 90 degrees of turn. But if you think about it, right, that the 90 degrees rotation, you do 190 degrees, you do two, and you do 390 degrees, right? Actually, each of them is the same because it's symmetrical, right? Like from 0 to 90, 90 to 180, 180 to 270. If we break it down into 3 parts, right? All these parts should have the same amounts, right, of EMF induced average, right? Because these things are all symmetrical. So basically what you're doing is you times 3 and divide by 3. So the average, in fact, for 270 has no difference if you just consider the coil rotates 90 degrees. Okay, so that's the first idea, that the average EMF of 270 degrees rotation, right? Assuming we start from like a flat position, right? Horizontal, and then you do like to flip into vertical, right? After the rotation, it should be the exact same situation as 90 degrees. Okay, so simply you just follow the equations you have learned. If you just want to find the magnitude, remove the negative sign. So I'll just put down and change in flux over change in time. So 200 turns, you sub the values in, right? And then yeah, it's simply assuming that the coil rotates for a quarter, right? So that would be, let's see, that would be the maximum. So hang on. Yeah, the started plane of coil is horizontal, so it doesn't really matter if it's from like horizontal to the field and then to vertical to the field. So minimum to maximum or maximum to min, it doesn't matter, right? Because you just take the value of big minus small, you do the greatest possible flux, right? That is the B times A. So 95 millitesla. So you times it by 10 to the negative 3, and that's B, right? That's B. You times it by the area. The area is nothing, but I'm going to change the units, right? So A would be 0.12 times 0.08 because we're going to change it to meters, right? So you change the centimeters to meters and you subtract this by 0, right? If you want to. So this is the change in the flux, right? And the time, right? The time is a bit more interesting because the hertz. So hertz, you can know that it's a frequency unit, right? Frequency, it's a 50 hertz, which means the period is 1 over 50, right? So for a full rotation, it takes 1 over 50 seconds, right? To do the full rotation, takes that much more time. But now we're not talking about the full rotation. a common mistake that the students made is they thought that 1/50 is what we sub into the time. Not the case, right? Because we're going to talk about is 1/4 of the rotation. So in fact, for here, you can do 1/50 multiply by 0.25. Multiply by 0.25, right? If you get all the numbers right, that should give you 36.48 volts, right? So that is the average, right? That is the average EMF induced in the coil, right? That is the average EMF induced in the coil. Okay, of course, right? If you rotate the coil a bit more, right, the total amount of EMF, the total amount should be greater than the 90 degrees rotation. But when we talk about the average, right, average across this period of time, then it is the same thing as rotate for 90 degrees because it's the average. So 36.48 volts. So I see that some of you in the chat got the correct answer. Very well done. For those who don't get it right at the start, I think it's because you forgot that, we're going to multiply it by 3, right? So I think you did something with the numbers. So it is the correct answer, but divided by 3. So that's what I'm observing. Again, it's a very tricky question. It's 36.48. So a lot of people got it correct. Lauren and Leo as well, There's no need to add the negative sign, Billy, because it's the order of magnitude, right? The magnitude of the average EMF, but it's very good, right? You paid attention to the equation that there's a negative sign before the n. So fabulous. Why is it 1/4, not 3/4? So because now we changed the scenario, Namra. So we changed it. So even if the question is asking what's going to happen for 270 degrees of turn, right? We simplify the scenario saying that actually, if you think about the average rotation, average EMF induced in this duration, it is the same thing as you rotated the coil for 90 degrees, right? Because look, what's happening is you, let's say, produce some EMF, right, in the first 90 degrees, you produce some other EMF in the next 90 degrees rotation, you produce another bits of EMF for the next 90 degrees rotation. But then you divide it by the 3 intervals, right? You rotate once, twice, and thrice. You divide it by 3 rotations so that the average is just the same as considering 1/4 of the rotation. So that is why we use 1/4, right? We consider the quarter of rotation when we approach this question. I believe you can do it the other way, right? But I'm just trying to simplify the scenario, right? Saying that this is exactly the same as a 90-degree rotation. Okay. So you can also think about 3/4 as a sinusoidal curve. That's exactly true. That the second and third quarter actually cancels out. Yeah, in terms of EMF, yeah, that's fine. That's I think is a valid answer, right? I think when it comes to magnitude, yeah, that should be all right. You can think in that way. That's a legit way to think. Yeah, that's fine. So let's see any other feedback. All right. Yep. So check in the chat. Yep. Thanks for all the questions. So to enrich our discussion. Okay. The next part. All right. The average energy dissipated by the lamp during this 270 degrees rotation. So in VC, there's one thing you should pay attention. It's somehow if you get the wrong answer here, right? So if you get not the correct answer, you use that in the next part, right? They should still award you marks for the correct substitution and the answer. We call this the consequential marking. It is very important. So guys, even if you miss out one question, right, give it a go, right? You can use literally any answer from the previous part and you can still guarantee to get all the marks in the next part. If you know how to do this part, right, not the first one, you can literally write down, the answer in part A is actually 1, and then use 1 and sub it in the next part. You can do that. That's the game rule. That's called consequential marking. So, say for example, let's say if you use 36.48, right, in the calculations, how are we going to do that? All right. So let's think about it. Average energy. So it is a different concept, right? So I would say this concept is like sort of just a little bit out of syllabus, but you should be able to do this. Okay, you should still be able to do this because when you think about energy, right, the first equation that pops into my mind, it's power times time, right? So you can think about average energy as average power times the time. And what is power? Right? we just kind of look at the information, what we got here, what we got in the first place. We have 15, right? We got 15 ohms. That's resistance, right? We also calculated the EMF, right? That's the average EMF. That's the average, right? So that's the average voltage for EMF over here. We can put the values in. So how do we express power in terms of voltage and resistance? Okay, so I believe you all know the equation, V squared over R, right? So you can use this equation, the voltage, average voltage squared divided by the resistance times the time, right? So in this case, we simply sub the values in, right? We simply divide the workspace into two parts, saying that the average energy is nothing but 36.48 squared, right? And then let me just erase this part, get rid of that. Go. And then times it by the time divided by the resistance. So 15, and resistance would be the 15 and then the time. Yeah, the time is the tricky one, right? So the time, it's this time for the duration, you have to think in terms of 270 degrees. You're going to think about 270. You can't use the first method that we simplify the scenario. The difference is because the first case, we're considering average EMF induced, right? This type of average energy. So we're going to consider the whole duration, all right, of this rotation, how much energy is created in there. All right, so I'll just put it in the words, right? 0.75 times 1 over 15. All right, so the answer would be 1.33 joules. Okay, so let me just read the question. What if I use 3 over 4 instead of 1 over all? You wouldn't get the same answer because it's different. Yeah. So I was saying that if you got like a wrong answer in part A, you can still sub the value, right? 36.4848. You get something like 100. You can sub 100 in to the next part if the expression is the correct substitution, you know. So if you get this part correct, let's see. So you get this part correct. So it doesn't really matter which value you sub in for this one. It's fine. You still get 1 mark for the steps. And if you get the correct answer, you still get 1 mark for that. Yeah, so Leo, good question. Does that mean 90 degrees and 270, they have the same average EMF? I would say yes, but I would put the word magnitude. All right, they have the same average magnitude of EMF induced. Okay, because as some of that, you may have noticed that the EMF is swap directions, and it's swap directions and the polarity swaps as they rotate. So this might happen. All right, so that's why I must emphasize it is the magnitude. All right, that changes. Okay, so for the next two questions, part C and D, I'm sure some of you guys are working on it already. Let's make it into 2 minutes, right? Because I want to see the sketch. All right, just 2 minutes for the two questions. All right, get your initial thoughts for the sketch. I'll keep answering the questions in the chat. So yeah, keep the questions coming. So Ralph, if you may set a 2-minute timer, that would be fantastic. All right. So let's see. Thanks very much. Okay, part C and part D. So one of the things that you all mentioned, it's very hard, right? You're struggling a bit with the graphs. So we're here to come and support you. All right, with some training. All right, it's about 1 minute left. So I'm pretty sure the first graph is pretty easy or straightforward to most of you. I think the second graph could be a bit more challenging. So if you don't mind describing a graph a little bit in the chat, right? Yeah, I think it's a harder question to answer in the chat, right? Typing the things out. But yeah, if you want to describe a graph, go for it. Go for it. Yeah, I am, and thank you very much. It is a cosine graph for C. We'll see if that's true, right? See if it's a cosine graph. What about part D? What do you think? All right, let's have a chat. All right. Okay, so I'm seeing some messages pop up in the main chat. Let's see. Okay. The first one is a cosine graph for C. Okay, so it is in fact accurate. You know, if we were to draw a graph, all right, that would look something like this. But change a different color. So the interesting thing is sometimes in VCE, actually most of the time, they asked for 2 full rotations. If you only draw one, I don't think they'll award full marks for you. So you're gonna have 1 and 2 cosine graphs. And more importantly, even they say a sketch, all right, it's good to put some markers in there, all right, about the time, you know, what time is it respectively. So actually you can do the markers before you do the sketch, all right. So say for example, in the middle here is say 0.01, this should be 0.02, 0.03, 0.04. Right, exactly right. If time, of course, in the unit of seconds, that's the case. Otherwise, just sketch the shape of the graph. That'll be fine. Okay, so it's a rather wavy cosine graph, and the reason is okay. At the very start, right? We began here with 0 flux because the coil was set to be horizontal with the B field. So there's no catcher. There's nothing going through the area of the coil. Okay, there's nothing going through that. So we started from no flux to some flux, right? So as the coil starts to rotate a little bit, right? It's not the best drawing, but bear with me. It rotates a little bit. We went from 0 to something, right? So that change in flux is maximum because in terms of percentage, right? From 0 to 1, right? That's a big change compared to like 99 to 100, right? Even though the increment is just 1, but in terms of percentage change, right? In terms of rate of change, 0 to 1, 0 to something is much more significant, right? So we started off the rotation with the greatest amount of EMF. That's the maximum EMF we're talking about here. All right. So we start from maximum and then just kind of follow the sinusoidal. Sorry, the cosine graph, right? The cosine graph, you draw it once, you draw it twice, and there you go. Now, I believe everyone understands the first one, but the second question, after rotating steadily for 2 minutes, for the y-axis, there's no need. It shows maximum and minimum, so that should be fine. If the graph is sketched, they provided these values for you. Just use that. Okay. So I believe it's a qualitative understanding. Good question from Billy. Okay. Let's see the next one. For part D, it's a very weird shape of graph. So it took a bit of time for me to draw that graph because there are 2 things happening, in fact. So even though it says rotate steadily and begin to slow down to a stop, right? It implies 2 things. So something you all may catch is that slowing down, Eric. So slowing down means you are increasing the period of rotation, right? So it takes longer, and longer, right, for the coil to rotate. That's one thing you observe. But I believe your teachers tell you the same thing as well, right? When you change the period or the frequency of rotation of a coil, not only does that change, but also the magnitude of the EMF generated changes. Why is that? Because by Faraday's law, right, EMF is proportional to the rate of change of flux. So I can see Sean's answer gets a lot of reaction. That is why, because 2 things, right? So apart from being a longer and longer period, which may look something like this, right? This is not the most accurate depiction of what's happening because the magnitude also decrease. All right. So yeah, let me just change it into something like this. So it's like a gradual change. Okay, so the question says two period, right? So sorry, two rotations. So I'm drawing two rotations, in fact, right? There's the first rotation, sorry, not here. There's the first rotation, you can see the second rotation. So you can see the time it takes, right? There's a huge difference between them, right? First and second rotation. So here you go, folks. That is the answer. And of course, I should be exaggerating a bit more about the change in terms of the magnitude towards the end. So if I were to further polish my graph, it would look something like this, right? So if I were to polish it, yeah, so almost dying off. You can exaggerate a little bit. So just to show that you understand that two things are changing, the magnitude of EMF and also the period, right? The time it takes for one rotation is increasing. Okay, so part D is a rather tricky one, right? Again, well done to everyone. Okay, Billy being very positive, for peers here. Well done, Sean. Question from South. Why is the EMF graph starting at the maximum? Why not the bottom? Because the n value in the EMF formula is negative. Ah, I see. Um, Look, I think it's okay, right? You can definitely draw the graph in like a flipped version, like a reverse version. It's just that sometimes in VCE, in the previous years of marking, there isn't much attention being paid to that. So, South, if we drew it in your way, right, you flip the graph along the x-axis, it's fine. You get the 2 marks for you, 2 marks for you, no questions asked. If you draw it like my way, right, starting from the top, it is still fine. Okay, and I believe the question says the magnitude, and perhaps that is why, you know, um, it's okay to draw in both versions. Although, yeah, I agree with you. The most accurate version is we had a negative EMF, right? Based on the given parameters, we start from negative, and then goes up. All I can say to you all is that sometimes, actually all the time in VCE marking regarding these graphs, they want to see the difference between like a sinusoidal graph and a cosine graph. All they want to know is which point to begin with. Is it the maximum or the minimum, right? And zero. Which point do you begin with? And what does the trend look like? Is it increasing? Is it decreasing? What is it like? So you must be paying close attention that the graph of EMF is never the same as the flux time graph. So two graphs should be different. They shouldn't be the same type of graph. You can't have two cosine graphs. You can't have two sine graphs as well. Okay. So yeah, hopefully for this question gives I guess a bit more insight regarding this question. Raf, how much time do we have left? Do we have time for another question perhaps? We can do a quick one.
Easy, yeah. Let's do maybe a slightly quicker walkthrough of deep dive number two, and should be good practice, Eric.
Yeah, no worries. Actually, I'm thinking deep dive number 3 because I think people are requesting um, for the questions regarding transmission, right? So actually, we do have a cover for that. Of due time, we can't cover all 16 marks, but once again, if you stay until the end, right, you get a link to download the solutions, right, the booklet for this webinar. So yeah, stay tuned. So maybe let's spend 2 quick minutes, to do this question. I guess let's focus on parts A and B. Okay, let's focus on parts A and B. I'll walk this through very quickly. All right, so we can make sure we finish it in time. All right, so how about this? Raf, let's say 2-minute timer, for those just want to think about methods, right? The method in solving this question. So let's do 2 minutes. All right, it's a bit challenging, but yeah, let's give it a go. 2 minutes to solve this one. There's less than a minute left. Okay, so yeah, I see some of you start posting answers there. Okay, so it's the ratio, so you can express in the ratio something to something, right? I think that's like a preferred format in mathematics and perhaps in physics too. So yeah, I think that's a correct answer from Billy just by estimating. Yeah, so just a quick question. Some of you requesting recordings, it will be done, right? We're gonna record it. We're gonna put it in a folder so you guys can get access to it. In fact, we're gonna upload this to YouTube. We're gonna upload this whole thing to YouTube so you can have access to it, in the spare time. Okay. 2 more seconds. Okay, let's do a deep dive. All right, let's go. So, what is missing in this question, everyone? What is missing here? All right, it's missing a diagram. Okay, so one thing we teach our students all the time is if the question doesn't have a diagram, you must draw something. You must draw a diagram because imagine you're going to do this paper for 2.5 hours. You can't put everything in your brain. Okay, so you must delegate some of the tasks to the paper that helps you to store a bit of information. So what I would definitely write down is what the transformer looks like. Okay, so it's a step-down transformer. Okay, stepping down from 20 kilovolts to 240 volts. Okay, so that is the voltage ratio. And based on the understanding for part A, we can find the turns ratio, MPNS, as equal to voltage ratio. So that should be quite straightforward. You do the unit conversions, you times it by 1,000, adding 3 zeros to the end over 240, right? So we usually present the ratio in like with the dots, right? So 275 to 3, that is the voltage ratio. Okay. So I'm seeing the questions, let's see. Yeah, so what's happening here? So if I were to make this very clear, this is what happens in the transformer. All right, some of you may notice. All right, Eric, is a bit different scenario from what you do usually because looks like the stepping down, after they step down, we have the transmission happening. We have the transmission happening. Okay, because it says that the transformer is connected to the substation by a 2-wire transmission line. Okay, and that transmits the power to the rural village. Okay, so this is where the transmission loss happens. So it's a bit of an interesting scenario. Okay, look, I may just do another part, part B1, right? For the remaining ones, feel free to go through the solutions to the end. Okay, so I may just do the B1 part, right? So I think it's very straightforward. Primary to secondary. The only tricky thing is you must reverse, right? It's like an inverse relationship because the higher the voltage, the lower the current to keep the power constant. Okay, so that is the case, which IP over 70 is at 240 over this number. So yeah, I think through this question, I want to show you guys 2 things, right? The one thing is the importance of having a diagram to depict what's happening. You always want to do that. And it could be different from the usual formats, right? The usual settings you face in your SAC or in your practice. So yeah, I hope through these 2 very quick questions can show you the importance of drawing a diagram. And yeah, I'll leave the remaining to you guys when you do a practice using the resources. And yeah, we're gonna do the gift drop very, very soon, all right, to give you guys the resources we promised to the end. So yeah, that's all from me. Yeah, Ralph, I'm gonna pass the time back to you.
Cool, fantastic, Eric. Yeah, thanks for the demonstration there. That was very, very good.
Yeah, thank you all for tuning in. And I will stop the recording for now.